Hello viewers, welcome you all. In this lecture, I am going to take the next unit of solid state physics, and the unit is band theory of solids. Band theory of solids, right? So in the earlier lecture, I have taken up the unit free electron theory of metals. You know very well that the free electron theory of metals was capable of explaining certain features of the solids, right? But when it comes to the main thing, that was why certain solids are behaving like conductors, semiconductors, and insulators, then free electron theory of metals have no answer to this question, right? So this theory was later on modified, right? And we have new theory about the solids that is known as a band theory of solids. So what is the difference between the band theory of solids and free electron theory of solids? So the main difference is that in case of free electron theory, we assume that the electron inside the metal or solid moves inside a constant potential that can be equal to zero, right? We have assumed, you have seen that in that case, we assume that electron are behaving like a free gas moving inside the metal, right, or the material, right, and they are facing no interaction except they are not allowed to leave the surface due to a potential barrier. So it was assumed there that the potential V in which these electrons are moving, it is constant, right? Even in the Sommerfeld quantum theory, we have assumed while solving the Schrodinger wave equation that B is constant and it can be taken as equal to zero. So this is the mistake that we have considered in free electron theory of metals, that the electron are moving in a constant potential, right? So when it was examined in details, right, then it is found that electrons are not moving in a constant potential inside the solid, but rather they are moving in a periodic potential, right? So if I look at the potential energy diagram, we know very well the potential energy of the electron inside the solid at a certain distance from positive ion core, that will be given by negative 4 pi epsilon naught, right, Ze square upon r. Here r is the distance of the electron from the positive ion core, right, and all these other factors are constants. So if I plot a graph, right, you can see here, if I plot a graph between the potential energy and V and the distance of electron from the positive ion core, let the positive ion core is located at this position, origin. This is positive ion core plus Ze, right? Then if we look at this equation, then according to this equation, what is the potential energy graph? The graph will be of this type. Similarly, if I approaches this side, then it will become, as the distance r tends to 0, this potential energy tends to infinity, right? So this is the graph. This is for one nucleus or one positive ion core. If I consider another core adjacent to it, right, this is the next core, right, this is the next core, then this is the next core, then this is the next core. All these are the positive ion cores inside the crystal, right? Then what will happen? You can see here. Then in that case, all these are positive ion cores, right? This is again plus Zd, plus Zd, plus Zd. So what you will get? You will get this type of graph there, this type of, right? Similarly, this one, it will become like this. So now you can see here the behavior of the potential energy with distance, right, when the electron is moving inside the crystal lattice, right. This is R and this is the potential. So you can see clearly from here that, and this distance, what is the distance? This distance, this is the lattice constant A, right, all. This is the minimum separation between the two adjacent atoms, right. So you can see here now the electron is subjected to the periodic potential, right. After certain interval, this potential repeats. You can see here in this range it is nearly constant, then it becomes extremely large, then again it is extremely large in this region, right, from here to here, then it is nearly constant, then again extremely large. So you can say that this electron is moving inside a periodic potential with its period is equal to the lattice constant. We can say Bx is equal to, oh, let me write it clearly, Bx is equal to Bx plus A. You can see from here it is repeating again, but our potential is here, the same potential is here, but our potential is here, same is here. So the potential is a periodic rather than it is a constant, right. So this was the main mistake that was made in free electron theory of metals. So this mistake was rectified in this Wand theory of solids, and this theory was most successful theory in explaining the Wand structure of the metals, right, solids. It explains why certain materials are behaving like insulators, semiconductors and conductors, right. But the basic approach in this theory was this periodic potential, right, rather than a constant potential, right. The first topic that is discussed in this chapter is this one, and then we comes to the Bloch's theorem. Bloch's theorem. Now we must know what is Bloch's theorem. Bloch's theorem actually is the theorem that tells us about the solution of Schrodinger wave equation when the potential, given potential is a periodic potential. I mean, if I write down the Schrodinger wave equation in one dimensions, d square psi upon dx square in one dimensional case, plus 2m upon h cut square into e minus b bx, right, psi is equal to 0. So this is the Schrodinger wave equation, equation number 1 in one dimensions, right, time independent, right. Now in this Schrodinger wave equation, you recall that Sommerfeld quantum theory, we have taken this potential V as constant and equal to 0, right. In Sommerfeld quantum theory, that was the free electron gas treatment according to the quantum mechanics. We took B as constant and for simplicity equal to 0. But here in this case, it is not equal to 0, neither it is constant, but it is a periodic. With periodicity, Bx is equal to Bx plus A. Here periodicity A is equal to the lattice constant, right. Now Bloch's theorem tells us that the solution of this Schrodinger wave equation will be of this type. Psi x is equal to e raised to power plus minus iota kx, right, into mu kx. This is the solution of this equation number 1, and the Bloch's theorem is this one. Bloch's theorem gives us the statement of the solution of Schrodinger wave equation when the potential is periodic, right. According to Bloch's theorem, the solution of this Schrodinger wave equation as it is written here, it is a plane wave, right, modulated by a function, right, modulated by a function this which has the same periodicity as the potential. I mean mu kx is equal to mu k x plus A, right. This is the statement and meaning of this Bloch's theorem, right. These functions e raised to power plus minus iota kx, right, this and this one, they are called as Bloch functions, right. So we have to remember that what is Bloch's theorem, what is the statement and meaning of this Bloch's theorem. So Bloch's theorem is simply related to the solution of Schrodinger wave equation in one dimension, or we can write it in 3 dimensions also, right. For that the things will get modified, and it tells us about the solution, and the solution is a plane wave, right, modulated or multiplied by a function that is also periodic, right. So this is Bloch theorem. Now I am going to the application of this Bloch theorem to the case of this, and it is done by Cronin and Penne in the Cronin-Penne model, right? So Cronin-Penne model, Cronin-Penne model. So as I told you that this model basically uses the Bloch theorem in solving the problem of electron moving in the periodic potential. I mean this case, right? So this model actually simplify the Schrodinger wave equation for the case of electrons motion in a periodic potential, and periodic potential according to this, I am drawing it here for simplicity. You can see here. Right, you can see here this is the direction of the potential, right, and this is the direction of distance, or x-axis or r-axis. So it is B, potential energy, Bx, right, and this is the distance r, right, toward this side. So you can see it is the origin, this distance is a B, right, and up to here it is a A, right. So and again this width is a B, right. So you can see here that the width of the potential, this is rectangular potential, right, and its height is B naught, and its width is V, right, and its period is A plus B, right. I mean you can see here that this is what, A plus B. So after A plus B distance, it is again repeating, right. So the period is A plus V, width of the potential is V, and height is B naught. So by solving the Schrodinger wave equation for this type of problem where the potential is a periodic, you can say, I told you that how it is periodic, right. They simplify the Schrodinger wave equation. I am writing directly the relation that they have derived, and then I will discuss the relation, and that is very important. The relation is P into sine of alpha A upon alpha A bracket plus cos of alpha A is equal to cos of K A, right. This is the solution that that we got after simplifying Schrodinger wave equation. Here P is equal to B naught, sorry, P is equal to not P square, it is P is equal to M B naught A B upon H cut square, right. This is P, right, and it is associated, you can see here, it is associated with, if we look at it, B naught B means the area of the potential barrier, right, B naught into B, area of the potential barrier. So P is somehow other things, M, right, A, right, and H cut, all these are constant, right. In fact, B naught and B are also constant, but they are representing the area, right. So P is linked with the area of the this rectangular potential barrier, right. So now I will discuss the meaning of this equation, right. K, I want to tell you the other things here. K is wave vector, right. A is lattice constant. As far as alpha is concerned, alpha is a constant, right. Alpha is a constant, right. Now, if I plot a graph between this side with alpha A, right, alpha A means this side is dependent on alpha A. You can see here, forget about this side, right? I am showing you that graph. This side is P sine of alpha A upon alpha A plus cos of alpha A, right? This side, left hand side of, like, this is equation number 1 for Cronin-Penne model, and this side here, we are plotting this side with alpha A, right? So now let's find what we have found after plotting this function as a function of alpha A. Look at this graph that I have plotted between the, P sine of alpha A upon alpha A plus cos alpha A. That is the left hand side of this equation, equation number 1 with alpha A, right? Now you look at equation number 1, because the right hand side of this equation of cos of Ka, and we know very well that the maximum value of the cos is plus 1 and minimum value is minus 1. So it means this side is limited, plus 1 to minus 1, right? It means if these two sides are equal, then it should be between, right, these two limits. That's why I have plot this this side, right, as a function of alpha A. But only those value of this side, only those value of this side will be allowed for which the value is between plus 1 and minus 1. You can see this red line graph. It is representing the plot of this whole term versus alpha A. But only those values are allowed which lies between these two lines, plus 1 and minus 1. So when we look at this graph, you can see here that this region from A to you can see from O to A, right, or simply let it is a M to A, right? This region is going above plus 1. It means it is not allowed, it is forbidden. Again, you look at this region from A to B. This region is between plus 1 and minus 1. So this region is allowed. Then from B to C, again it is going outside minus 1. It is forbidden. Then C to D, allowed. D to E, forbidden. So you can see very, very important result that we got from this graph, that the graph contains some allowed energy bands and some forbidden energy bands. What I did, I plotted P sine of alpha A upon alpha A versus this. I told you that here alpha was equal to, actually alpha, we have put alpha in the Schrodinger wave equation, alpha square is equal to 2me upon h cut square, right? So we can say it is the energy, it is related with the energy. Alpha square is equal to 2me square 2me upon h cut square. So alpha is directly linked with the energy. So we can say that it is a E versus alpha A graph, right? So this graph, give us the idea, give us the result that the energy spectrum of the solids contains allowed energy bands and forbidden energy bands. You look at this graph. As the value of alpha A increase, you go to this equation. When the value of alpha A increase, it means this factor will become negligible. Alpha A in the denominator. Negligible, I can drop it. Then simply this cos of alpha A will be cos of Ka. So in that case, when we plot the graph of cos of alpha A, it will simply lie within the plus 1 and minus 1. The case of going outside plus 1 and minus 1 didn't arise. So in that case, the allowed energy bands will increase and the forbidden energy bands width will decrease. And if it becomes 0, then we will not get forbidden energy bands. And in that case, if we apply this condition, we will simply get E directly proportional to K square, because in that case, cos of alpha A is equal to cos of Ka. So when we simplify it, we will get E directly proportional to K square, or E is equal to H cut square K square upon 2m, right? So this is the case that we will get for the extreme situation when alpha A tends to infinity, right? This tends to infinity, right? So in that case, the forbidden energy bands will disappear and the allowed energy bands will become maximum. But in general, as we are going away from the origin, the value of alpha is increasing, then the width of the allowed energy band is increasing and the width of forbidden energy band, you can see here, this is decreasing as we are going toward this side. Now it is much wider than this one. You can see this one, right? As we go further, then this width go on decreasing, and ultimately when alpha A becomes infinity, it will become 0. This is a very, very important result. And for the extreme situation, we will get E is equal to H cut square K square upon 2m, that is E directly proportional to K square. And this is the same case as we got for particle in a constant potential or a zero potential, right? We can convert this equation. E is equal to H cut square upon 2m into n pi upon a whole square, right? So this is the result of this Kronig-Penne model, right? It is very, very important. This graph is very, very important, right? Because the idea that we got about the semiconductor, insulators and metals, we got from this graph, right? This equation, and then we plot this equation versus alpha A, and then I arrived at these results, right? Now I am going to the next topic, that is effective mass of electron. Effective mass of electron. Effective mass of electron means while moving through the crystal, the electron behave differently than a free electron, right? It can be assumed that sometime it is behaving like having positive mass, or sometime having negative mass, or sometime having mass very, very high, right? Even its magnitude can change, right? So this mass that is exerted or possessed by the electron while moving inside the crystalline solid, right? That is known as the effective mass of electron. I am writing its expression directly. We have to remember it. Effective mass of the electron is defined as m star is equal to h cut square upon d square E upon d k square. So this is the expression for effective mass of electron, right? M star, we call it effective mass. And very important result that we found from the effective mass of electron discussion graph, that in upper half of the band, it is behaving like a particle with negative mass, right? Or we can say as a whole also. So we have to remember it. In the lower half of the band, it is behaving like a particle with a positive mass, right? And when we look at the origin, or we can say at the point of inflection, right, where we are going from lower half to the upper half of the band. So at that point, the mass of the electron, that is effective mass, it becomes infinite. I told you that different situations can be there inside the crystal. At the point of inflection, right, where we are going from lower half of the band to the upper half of the band, the effective mass becomes infinite. In the upper half of the band, it becomes negative. In the lower half of the band, it is positive, and its magnitude is this one. It can be equal to the actual mass of the electron. It can be greater than or less than the mass of the electron, right? This is very, very important result. We have to remember these different situations and this expression, right? Now I am arriving at the last topic, of this chapter, that is the distinction between metals, insulators and semiconductors. So we are doing this distinction or difference on the basis of this band theory of solids, right? So according to band theory of solids, I'm not going into all discussion, but our results we found that in case of insulators, there is a wide gap between the valence band and conduction band. This is conduction band and this is a valence band. So there is a wide forbidden band, right, of the order of 10 electron volt or more, right? We call those materials as insulator, right? But if this band is small, it is less than 10 electron volt, right? Then we call that material as a semiconductor. If it is less than 10 electron, I mean 1 electron volt, 2 electron volt, 3 electron volt, then we call that material as a semiconductor, right? The forbidden band limit is between 1 to 10 electron, even it can be less than 10 electron volt, but for most of the semiconductor that we see in the nature, they have the range in between these, right? Sorry, energy limits. And as far as metals are concerned, it is found that in case of metals, there is overlapping between the valence band and conduction band. So when there is overlapping, large number of free electron can go into the conduction band, can act as free electrons, right, for the conduction of electric current, right? So we have to remember all these situations. So you can be asked that what is the width of forbidden energy band in semiconductor or in conductor or in insulator. So this is the difference that we made on the basis of band theory of solids. We can also say that in case of insulators, all the bands up to valence band are completely filled and all the bands above this band are completely empty, right? And the difference between filled and the difference between these two or gap between these two is of the order of this. This is the situation of insulator, right? For semiconductor, the same situation is there, but the conduction band is not fully empty. Some of the electrons had moved from here to here due to the small gap between the valence band and the conduction band. So there is also vacancies in the valence band. All the levels are not fully filled and there are presence of some electrons in the conduction band. But in case of metals, right, all the electron in the valence band that are going to act as free electrons, they are present in the conduction band because there is overlapping of valence band and conduction band. So these are some important points related to this chapter that I have covered, band theory of solids. Three important things are there. First is Bloch theorem, then Cronin-Penne model, then effective mass of electron, and then finally the distinction of different solids on the basis of band theory of solids, right? So thank you very much.